Hi and welcome back, and now we are going to deal with the first example of recursion, that is how to compute the factorial of a number. So we have already seen that f of n for factorial can be written as n multiplied by f of n minus 1, and for example if we have 5 factorial, it can be written as 5 into 4 factorial. And we discussed when we are going to solve a recursive problem, we will figure out two cases. One is a base case and second is a recursive case. Okay, so in the base case, I know when the value of n is equal to 0, the answer of factorial should be 1, and in the recursive case I know the formula is nothing but n multiplied by f of n minus 1. So these are the only two things that we need to know. So once we know these two things, we can write the code, and while after writing the code, I will tell you how the call stack works and why we are getting the right answer. Okay, so we will also talk about call stack in recursion and why it is correct. So let us first dive into the code and then we will see. So I'm going to make a recursive program for factorial. So let us say we have a function int factorial. The return type is integer because the function is going to return an integer. So we get some value input, and we have a base case, and we also have a recursive case. So what is going to happen in the base case? We are going to say if n is 0, then we know the answer is going to be 1. That's it. In the recursive case, we know that the given problem f of n can be written as n multiplied by fact of n minus 1. That's it. And we can say return this answer. And we are done. Okay, so this is the complete factorial program. And now we are going to test our code. So maybe take input from the user and print the factorial of that particular number n. So build is successful. So let's run it. So if I give 5, I get the answer as 120. If I give 6, the answer is 720. That means it's working perfectly fine. And now let us also look what happened actually. So when your program started, okay, so there is a call stack, there is a concept of a call stack. So what is call stack? Stack is a special memory, so it's like a container, and all the functions that are called, they go inside the stack. So first of all, the main function, it went into the stack, and all the local variables like n, here we have only one local variable, so that is defined here. And let's say we took this value as input, so n is defined as 5. So from here we call the fact function and we tell, okay, we have to compute the factorial of n equal to 5. So this checks whether the base case is true. So this is not true. It makes another recursive call. Okay, you can see it computes a value answer. So there is a variable answer that is not yet computed. So it is 5 into something. So that something is what? That is factorial of 4. So we make another recursive call to the factorial. That call gets pushed into the stack where n is 4. And here we also create another local variable because answer is a local variable. Okay, so in every call stack we are going to create these local variables. So here the value of answer is 4 into something. That something is another function call, will return. Okay, so n equal to 3. Here we have answer equal to 3 into something. That something is nothing but another function call. N equal to 2. Answer equals to 2 into something. That is f of 1. So we make another function call, and that answer is 1 into 0 factorial. So we make another function call with n equal to 0. So now when n is 0, we say return 1. So this function actually returns 1. It gets removed from the call stack. So here I will change my color. Now we are going to work in the different direction. Now we have reached the base case. Okay, and the base case says you return 1 to the point from where it was called. So it was called from here, so we return a 1 here. So it becomes answer is 1 into 1. Now f of 1 is going to return 1, and you can see return answer. Now this statement, earlier what happened is when you were computing this answer, this function was paused at line number 12 and it was waiting for the value of fact of n minus 1. Okay. Once it got a value from fact of n minus 1, it returned the answer, that is 1 into 1, that is 1. So this gets removed from the call stack and this answer 1 is stored here. So it is 2 into 1. Now this function was waiting for the value of f of 1, and now it has got the value because this function returned to its parent. This will get removed, so it will return 2 into 1, that is 2. So 2 will come here. Similarly, this function was waiting for f of 2. Now that value has arrived and it will return 6. So 6 will come here. So it would become 4 into 6, that is 24, and it would return 24 here. It would become 5 into 24, that is 120, and this value would come here because main is waiting for this value. So here you will get an answer of 120. That's it. And finally, once your main is also over, this also gets removed from the call stack. Okay, so if I talk about how much time it will take, so we actually made a call stack of n levels deep. So we are making n number of calls. Each call takes constant time, so the time taken is order of n. Okay, so time is order of n. And what about the space complexity? Okay, so if I talk about how is the space complexity changing throughout the entire program, so initially you can see there was only one stack frame, that it increased to 2, 3, 4, 5, 6. Then it came back to again like 0. So during the point when the base case was hit, the space utilization was maximum, and that was equal to order of n. Okay, so in the worst case, or during this entire execution, so this is space and this is time of execution. Okay, so at a particular point the space utilization was maximum, so we would say the space complexity of this program is also order of n. Okay, although we are not taking any extra array, but we are using the call stack which takes memory, and you can see for maximum depth of n, we have created n number of answer variables, each storing a different value. Okay, so at a particular point in the program, the space utilization went up to linear. So we can say both space and time are going to be order of n for this problem. And one point you need to remember, that all recursive problems will take up extra space. Okay, so recursion actually takes extra space because of the concept of this implicit stack. Okay, so that's it. That's all for this lecture, and now I hope you understood how recursion actually works for this particular problem.